Let's now look at the electric potential from a point charge. We already looked at a parallel plate capacitor because that creates a uniform electric field, which is kind of the simplest scenario to think about, but obviously the point charge is a little more fundamental. So if we take the potential energy of 2 point charges, which was something previously determined, we can use that to get to what the electric potential from 1 point charge is. So remember that we need to clearly determine what our source is, and in this case we're calling Q our source. So to find what it is, distance r, from our source charge, we're just going to place another charge there. So this is our test charge or our probe charge. So we know what the potential energy of this system is, which is what we got here. And so that's why we're dividing out Q prime, because we were actually trying to find V from this configuration. So again, remember that we must determine what our source is versus what our entire system is. The system is the source plus whatever additional object or charge you're placing. So in the end, the electric potential from a point charge is Q over R, where R is the radial distance, whatever distance you are from that point charge, with our normal factor of 1 over 4 pi epsilon naught. So briefly, one of the things that's a little bit tricky to keep in mind is that electric field and electric force went as Q, or both Q's, over R squared. Electric potential is just 1 over R. So these equations look really, really simple, but when you go to do the math, make sure that you correctly are using 1 over R or 1 over R squared, depending on whether you're talking about electric potential or electric field. Part of why you have an equation sheet is so you can always double check that and get that correct, so be careful about that. So let's now look at our visualizations. And again, we met these 4 types of visualizations with our parallel plate capacitor. And now it's a little more interesting to think about what's going on with our point charge and the potential now. So I'll briefly talk through these and then again I'll zoom in on pairs. So our potential graph, we are looking at the radial distance. And remember that this goes as 1 over r, so what you see is that as r goes to infinity, our potential is going to 0. And so if we imagine this going really, really far out, eventually this line would reach it. And this is for a positive charge. If we had a negative charge, this would all be negative. Note that as r goes to 0, that means our potential is going to actually go to infinity. So that's just the behavior you're going to get for a 1 over r sort of curve. So that's what the shape looks like, and this is important to understand. It's not constant, and it's certainly not a straight line. Then we can think about our equipotentials and our contour map. Now remember that here we haven't actually really put any numbers on them, right? But we can start trying to label them, and note here it's been in terms of just some V1. So if this is V1, our next line needs to be at even multiples, so we're going to call this V2, which just equals 2 V1. And then this most inner one is going to be 3 V1. So their spacings are equal in terms of the potential, but notice that their actual spatial spacings aren't equal. I think that's easier to see here in the contour map than the equipotential surface. This little window here is just so you can see, because otherwise all you would see is a sphere. Obviously, the surface would continue to be filled in there. I don't think it's very easy to see what's going on in these equipotential surfaces. You can't easily tell that they're not equally spaced. Again, this radial distance here is actually, changing quite substantially. But you see that you do have a spherical symmetry. So imagine this contour map being rotated through space, and that would give you your equipotential surfaces. Another thing that's helpful to look at is this elevation graph. Note that these little squares are put on just to help you better see what's going on, and obviously this would be really hard for you to draw yourself. But we can look at the picture in the book. Sometimes you're going to see colors on it just to help you better visualize what's going on. And again, our point charge is like right in the center, right? And here the upwards represents V. So we're seeing a two-dimensional plot rather than a fully three-dimensional plot. And again, you see that there are circles that represent places that have the same potential. And again, this would be 3V1. Here we have 2V1. And here at the bottom, we have V1. And again, as you get further and further and further away, it goes to 0. So when you think about drawing this, you should think about the potential graph and the contour map. So remember that this 1 over r means that you would actually have to go, even further out to find the point where it's, say, v1 over 2. But we wouldn't necessarily draw that as a contour here if what we're trying to do is show equally spaced points, right? So these 3 points, this one corresponds to that. We can show another one that would be up here at 4v1, and when we think about it, that would be roughly here, or maybe a little bit lower. So remember that again, you're not trying to space them equally in space, but you're trying to actually find them where they're spaced equally in potential. And so this delta r is not the same as that delta r. And that's a little bit harder to see on the elevation graph. So this elevation graph is effectively taking the center point, which corresponds to r equals 0, and then just tracing out, let me switch colors, tracing out this curve, right? So we're just taking one spot, tracing out the edge of that, and that's what's coming out over there. So this is what you should be ready to draw. Now again, if we think about our equipotential surfaces, we can basically try to imagine taking these nested spheres like an onion, cutting through them, and looking at them edge on. And each one of these circles then corresponds to the edge of one of these spheres. And again, the radius that you see here is not equally spaced, but this is again your V1, 2V1, and 3V1. If I wanted to draw another circle, you can't draw it in between here because then that wouldn't be equally spaced. You can't even draw another one further out. That isn't to say that our potential is 0 here, but if we went 2v1 down to 1v1, another step would be 0v1, which is all the way out infinity. So our next increment, if we wanted to draw another circle, would have to be 4v1, and that would look somewhere, and that's a terrible circle, but somewhere here. So you know that they're going to get closer and closer spaced to each other, and you would have to have infinite V1 before you actually reach the point charge itself. Keep in mind that this is a point charge, so you'd want to think of it as infinitely small, not actually having that size. So lastly, we can think about a sphere. So not necessarily a point charge, but an actual charge sphere. So if we have radius r, as long as you're outside of the sphere, this actually looks really similar to a point charge. Again, there is a relationship between the electric potential and the electric field, and we know that the electric field outside of a sphere is identical mathematically to the electric field outside of a point charge. So the same holds true for potential as well. And again, there is a deeply mathematical reason for that. Now, what about inside of the sphere? And we will talk more about this when we connect electric field to electric potential, but I want to tell you one thing at least right now, which is if the electric field is 0 inside the sphere, and why might that be true? You might have a solid conductor, or you might have a hollow conductor, like a bubble. As long as there's no charge inside, we know that our electric field is 0, and that means our electric potential is constant inside. So at the surface of the sphere, we can define it to be V0, and then our V0 that is constant inside equals that surface, right? So this is V of the surface, and then this is V with r less than the surface radius. That is only true again if the electric field is 0 inside, which is true in some situations. Note that that is different than saying that electric potential is 0. So if our electric potential is 0 at infinity, At the surface of the sphere, it is not zero, and then inside the sphere, it's not zero, but it's the same as the surface. And again, the next chapter will allow us to tie that together.